Okay, this should be video PS for physical science 3-4, which is the 4th week. B for the second video of the week, Blake. PS34BBlake. Okay, so I was like, let's say you're up here on a tower and you drop an object and it falls straight down. And you throw an object out and it falls down. And you shoot an object out like a bullet and it falls straight down. We established, and I showed you on the last set of videos, if you drop an object to shoot one out, they're going to hit at the same time that this one's going to hit out here. If you shoot an object, a bullet, it's going to hit two at the same time, way out there. Now, I've had students try to argue that with me before, but if you set up experiments and do it, that's just a fact. The sky's blue, grass is green, that's the way that happens. So maybe I can set that experiment up for you and show that to you, but you're going to have to accept that because it is factually the case. Now, let's do a thought experiment with that. Let's zoom out. Let's zoom out to the point where you start to see the curvature of the Earth. So zoom out several miles. And then you have that tower. Let's say you shoot a bullet out and it lands out here, and you shoot another bullet out and it lands out here. This is going 1,000 feet per second. This one's going 3,000 feet per second. This one's going 5,000 feet per second. This one's going 10,000 feet per second, or something like that. Now there starts to be a difference because they're going so fast. And let's take air out of this, because air is going to slow these bullets down. But over a long distance, now we've got the curvature of the Earth coming into play. And that's a whole different discussion. So the faster this object goes, and the farther it goes in that amount of time, now the curvature of the Earth has to come into play. And this one actually has to fall farther than these do. And it's going to be out there for more time. And if you can go fast enough, so let's zoom out more to where you have the Earth, and you shoot that way out, it's going to come and hit way out here after the Earth is curved quite a bit. If you shoot even faster, it's going to go quite a bit farther before it lands. And this is what you see if a spacecraft comes back. You know, they fire the rockets to slow it down, hits the atmosphere about out here, and it'll fall. You know, they'll start bringing those down over the Indian Ocean to land it in somewhere in the U.S. Maybe they used to land these at like on the desert flats. The space shuttle, they used to at first do that. So what would happen if you shot it fast enough is, bang! It would go and go and go and go and go, but it would fall and fall and fall, but it would never get there. It'd be coming at you from the other side. That's basically what orbit is. You shot an object out so fast, and it's falling and falling and falling and falling and falling and falling and falling, but it's never getting to Earth. It's just staying at the same altitude because you hit orbital velocity, which is about 7.5 kilometers per second, which is around 5 miles a second, and about 17,000 miles per hour. Now that speed's going to vary depending on your altitude above the atmosphere. The atmosphere is actually really thin around the Earth. You're 100 miles up, which isn't very much considering this is 6,380 kilometers. You could add another 100 kilometers to that, and you could orbit there for a while before you hit enough molecules to drag you back down. So that's not much. The Earth's atmosphere is very thin by comparison. So that's what orbit is. You are basically falling around the Earth. So objects in orbit and objects in other free fall experience weightlessness. When you're at that ride at the amusement park and you feel weightless for a second or 2 seconds, that's because you're falling. Maybe they get you started up and you're going over the hill on a roller coaster and you feel weightless for a second. To get you to feel weightless, you're probably never going to feel weightless for more than 2 seconds here on Earth, because your speed just gets so high. Now, those objects that are out there orbiting or free falling still have their mass. You know, when they crash into the ground, they're still going to leave a crater. But there's nothing pushing on them against gravity to make them feel the acceleration that's changing their velocity. So if you've got a person in an elevator and then everything's sitting still, they've got to wait. You cut the cable, let the elevator free fall, and the person in it free fall, and the balance in it free fall, the scale in it free fall, they're no longer pushing on this scale. They'll fall to zero for a little bit. And that's not going to happen in a real elevator, we hope. Okay. But let's go on. All right, you've had rides like this that whirl you in a circle. And that's making a different kind of acceleration, one we're not going to run into in the lab here. You are being pushed into the shape of a circle. Or if I was driving careful this morning around the curves because they're slick. Because if the road is slick and my friction stops, I'm going to go that way. Continue in my path. The road's going to continue to curve. I'm not going to be on the road anymore. It'd be the same thing if satellites were in space and gravity shut off. Whatever that motion was they had, they'll just keep going that way. So the road, when you do this, is actually grabbing your car's tires and pushing them to the center of a big curve, a big circle. That's called centripetal acceleration. Now you might call that centrifugal force doing that. That's not a real thing. That's a product of inertia. So let's do a straight line thing. You're at a stop sign in a muscle car, and you hit the gas and take off. If you've ever been in that situation, it feels like the seat is shoving into you. Or it feels like you're being shoved into the seat. But you're not. It's the seat shoving into you. You perceive that you're being pushed into the seat. But really, the seat is pushing into you, making you go faster, 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 faster. A similar thing is happening here. Your body in this car wants to go in this path. But the road pushes the tires, and the tires push the car, and the car pushes the door, and the seat belt, and the seat and everything that pushes you this way. And you are pushed to the center of a circle. That is called centripetal acceleration. You perceive that you're pushed that way. And we call that centrifugal force, but that's not a real force. That's your inertia wanting to do what it does. So a centrifugal force is not the force that's changing your motion. It's a perceived force. It's a virtual force. The real one is centripetal. And what's happening here is the back cage of this ride is forcing people to be spun towards the center of that circle. Okay, kind of the last topic here. Momentum is mass times velocity. We've already done a calculation on that last time we had video, I think. And the law of conservation of momentum says, I give momentum to a ball that hits this stack of pool balls. They go every which way, but if you add that momentum and 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 that momentum, you get the idea. If you add all the momentums of all the particles up, the total is what you started with the cue ball. So the total momentum doesn't change, and that works pretty good actually. The conservation of momentum holds. That's why it's a law. So let's say we shoot a cannon. The ball goes zing that way. The cannon goes back this way. You may have experienced that if you've shot a firearm, a shotgun or something. It's got recoil. When that cannon is sitting there, it's got no momentum. Momentum is zero. So if we give the cannonball a big positive momentum that way, the cannon's got to have a negative momentum that way that's equal to it. So the total is still zero because of the law of conservation of momentum. So let me give you an easy way to do this. If that cannon is 100 times the mass of the cannonball, what's going to be true about the motion of these? Aha, the trade-off, if this is 100 times more massive, that has to be 100 times faster. So if the ball's mass is 4 kilograms, and the cannon's mass is 400 kilograms, and the cannon's rolling back at 3 meters per second, what's the ball going at? Well, if that's 100 times the mass, 400 compared to 4, that motion has to be 100 times 3, 300, right? Well, they're the same. You can also get it this way. Because that momentum negative and this momentum positive have to add to the original 0 they had when they were sitting there. When I take that to the other side, they're equal and opposite. So a way to do it is if the cannon is 400 kilograms and its velocity is minus 3 meters per second, because that's left, and the cannonball is 4 kilograms, what does the velocity end up being? Well, you take 400 times minus 3 and divide it by 4, you'll get 300. So, on paper, try that. Oh, well, let's talk about this first. So let's say you're at the lake and you jump off a inner tube. What happens? You've tried this probably if you can swim. You jump as hard as you can. Pretty much you just plop down. Why? Because that's low mass and it just shot out. So you weren't able to give it that much momentum. You didn't get much momentum forward. You plop down, it goes this way. But what if that's more massive? Maybe you've tried this. You jump off a rowboat. Well, now let's say its mass is about yours. You get some forward motion and it shoots back some, not as fast as this. So you both get an equal momentum here, it's just not very much. You both get a momentum here and your speeds are about the same because your mass is about the same. What if you're on vacation and you're on a houseboat and you jump off the houseboat? You go out here pretty fast. Does the houseboat move? Yes, but real slow. So if the houseboat has a huge mass compared to you, you're going to have a big velocity compared to its little velocity. And the bigger this object is, the slower it moves. So what if you were jumping on the earth, which is enormous? And let's say you had a mass of 100 kilograms. You're a running back for a pro football team. 220 pounds. And you can jump at 6 meters per second, which is a pretty fast jump. You're going to have a momentum of 6 times 100 is 600 kilograms times meters per second. But the Earth's mass is about a 6 followed by 23 zeros kilograms. 6, 0, 0, 0, 0, 0, 0, 0. You get that. The mass is enormous compared to this. What's that velocity going to be like? Not 0. It's going to be 600 divided by this enormous number, which is going to give us a tiny velocity that's too small to measure. But nonetheless, it exists. So if you're jumping up and down on the Earth, you're giving the Earth a tiny amount of momentum. Now there's all kinds of other objects moving in the Earth. Nobody's going to detect this because it's going to get lost in the shuffle. It's going to get lost in the noise. But it still exists. And your velocity, because you divided by this enormous number, would be 0.000000000000000000000000001 meters per second. Too slow to detect. But it's not 0. And a rocket does a similar thing. The rocket pushes the gases this way real fast, but they're really low mass. And because it's got a big mass going this way, it only picks up a tiny amount of velocity each second. And those pushes are equal and opposite. And the momentums are equal and opposite. So when the rocket first fires up, why do the gases travel so fast? Because their mass is tiny. Their velocity is huge. The mass of this is huge, so its increase in velocity is going to be much smaller than the gases are. We'll watch a Saturn V launch. Okay, here's a number line question I want you to try. You got a rocket booster propelling a satellite. It's up to altitude. It's ready to shut off. And so for the last couple of seconds, it's going to 7,500 meters per second. And it's exhausting gases at 5,000 meters per second. What is the velocity of the exhaust gases relative to Earth? I want you to think about that. That's an interesting one. Okay, so if your rocket is shooting gases out, and the rocket is in 1 second, the rocket is 1,000 times the mass of the gases that got shut out, then the gases are going to have to go 1,000 times as fast, increase in velocity, as that did in a second. And start page 92, number 22 to 28.